Okay, so today we're going to talk about what we call the effect of individual observations on the fitted regression model, and this is getting at the idea that sometimes just one or a few or a handful of observations can have an outsized effect on the kind of model we end up with. So the goal of today is to look at when that happens and what are some ways we can detect that. Okay, so we'll title this the effect of individual observations. Okay, so sometimes one of the observations, or a few of them, an observation, or a few observations, can have a large impact, or what I'll call an outsized impact, because of course every observation contributes to the fitting of the regression model, but what we're saying here is that some could have a larger effect than other observations. Okay, so that's what I'm calling an outsized impact on the fitted model. Okay, and so often these are what we call outliers. So first, I'm going to basically walk you through three concepts that are related to this. We're first going to talk about outliers, then we're going to talk about leverage, and finally influence. Okay, so let's start with outliers. So I think many of us already have an intuitive understanding of what an outlier is. It's an extreme or otherwise unusual observation. Okay, so we will say that an observation is an outlier if it's substantially different than what's usual in the rest of the data set. Okay, so formally, so let's say observation. So what is an observation? We're talking about, let's say, observation I, which would consist of the response, yi, and its associated predictors. So just write them out, xi1 up to xi p. Okay, so we say that is an outlier. If it is quite different, it is, say, substantially different from the rest of the observations and the other. Okay, and so when we say it's substantially different, there can be, well, we will classify it into a few cases. So in words, let's first point out that this can occur. Okay, so the response value could be extreme for a given set of predictors, or some of the predictors might be far away from the rest of the observations. Okay, so let's state that first. If its response or some of its explanatory variables have values that are quite unusual. Okay, so that are unusual or extreme. Okay, so often it's best to illustrate with the simplest case where we just have simple linear regression. So let's draw a picture to illustrate this in simple linear regression. Okay, so let's start with the plot. Okay, so let's suppose we have some points. Okay, so here is most of our points, and we suppose we're going to fit a regression line to them. Okay, so what would outliers look like? So let's give you some examples. Here's x and here's y. Okay, so most of the points are around here. So suppose we have a few outliers. So I'm going to draw a couple examples. Okay, so let's put this blue point here. Okay, I'm going to call that A. Alright, so this point, relative to the rest of the points, if we had an observation that had a y value here, this would be considered an outlier. Okay, we can see from the picture that the value of the response is far from what would be expected based on the rest of the observations. A y value here would be considered quite unusual or extreme. Okay, so this would be okay. So let's write that in words. So this point would be considered an outlier in terms of having an extreme value for the response. Okay, so the x value is well within the range of the other points, but for that particular x value, most of the other points are down here, but then we have a recorded response value that's all the way up here, so that's considered an outlier in the response. We could also have outlier in the second case, in an explanatory variable. So here we only have one explanatory variable. So for example, if I had a point all the way out here, okay, so let's call that point B. Okay, so this is also an outlier. Okay, and the value of the response is sort of within the range of what the rest of the points have, but the value of x is way out there. So the value of the predictor or the explanatory variable would be considered extreme or unusual for point B. Okay, so let's again label this. So this is an outlier in value of the explanatory variable. Okay, and finally, of course, you could have both of these together. So what would be an example of a point that is outlier in both the response and the explanatory variable? Well, let's put a red point. Let's put it up here. Okay, let's call this point C. All right, so this one is an outlier in both the x and the y dimension. Okay, the value of the response is unusual and extreme, and so is the value of x for this point. Okay, so again, we'll label this one. So this one is the red point is an outlier in both the response and the predictor. Okay, and the reason we distinguish it is it's going to, we can detect and characterize these sorts of outliers in different ways. Okay, so keep in mind that this picture, and I'll try to leave it up here as we describe the various characterizations for these points. Okay, so but first let's make a few comments about outliers in general. Okay, so why do we get outliers sometimes in our data? So outliers, so there could be nothing, just because you have an outlier doesn't necessarily imply that we have an error, although that could be one of the possibilities, like a data entry error or a measurement error, like a typo or you add an extra zero or something. So that could lead to an outlier, but often it just happens that you have an A subject, for example, in your study, and there's nothing wrong with the recorded values. Okay, can happen can occur for different reasons. So you might, for example, nothing is wrong, and you just have an extraordinary subject in your study. Okay, so then that's really just part of it. That's really part of the data. There's nothing to worry about in terms of whether the data is correctly recorded. But it can also be because of human error. So we can call, for example, data entry error. Okay, so generally we don't arbitrarily throw away our data. So I should point out that we don't recommend just throwing away outliers, removing or throwing out outliers, unless we have a good reason to. Okay, so we have some strong reason to believe that it was an error. To believe that observation is an error. Okay, but definitely worth looking into because, as we'll see, sometimes outliers can affect the fit of the regression model. So one point can really pull your regression line away from the rest of the points. Okay, so that's why we're calling this the effect of an individual observation. Okay, so unless the observation is an error and does not belong in the data set. Okay, but nonetheless, it can be useful to investigate, well, since we have this sort of special or unusual point, how does it affect our regression estimates? Okay, so let's make the second point is why it can be useful. To investigate what effect it has on our model. It has on our model. Okay, so a fitted model could change as a result of outliers. So it could be useful to investigate to what extent it affects the model. For example, if we want to do prediction and most of our points are here, and if an outlier drags the regression line away because we're doing least squares, so it's going to have an effect on the slope estimate. So it could hinder our ability to predict, for example, for the rest of the points. And so therefore we can investigate that to an extent. You would like the webcam a little bit to the right. Okay, let's try. Okay, hopefully that's a little better. Okay. Okay, so what I was saying here is we can investigate what effect it has on our fitted model, and as I said, if it changes the slope, for example, you put point B into your regression model, it will likely shift the regression line a little bit and reduce the slope, and so it might not go through the rest of the point as well. So So to say that in words, we can investigate what effect it has on our model and also the quality of the fit of model fit to the rest of the data. To the rest of our data. Okay, so with that in mind, let's discuss a few ways of detecting this sort of issue. Okay, so first, that was the first concept was what is an outlier. Now, secondly is how do we distinguish what kind of outliers are potentially in our data? How do we characterize them? And how do we know what impacts they have on our regression model? Okay, so let's move on to the next idea. Okay, so the next few points are about how to, so concepts related to how we can detect and characterize outliers. Okay, I think my black is sort of dying, so I'll try a different pen. Okay, so that was point one. So there's a second concept. So this one actually is not new. Okay, so we had when we talked about residuals and model assumptions, we introduced what we call a studentized residual. Okay, we call them. Okay, so just to remind you, we call them DI. And how we get them is we take the residual. Okay, so EI is the the residual for the ith observation, and we do a sort of standardization. We divide by sigma hat and 1 minus h sub ii. Now, what is this? So let's remind ourselves. So we have h sub ii, which is coming from the hat matrix, which we've called capital H. So these are the studentized residuals. Okay, so why are these useful? Well, remember that we call that the residual EI has a normal distribution from our derivations. It's mean 0 and variance sigma squared, 1 minus the ith diagonal element of the hat matrix. Okay, so therefore these guys, these studentized residuals, as you notice, it's like standardizing. Okay, we're dividing by an approximation of this, the square root of this. Okay, so that basically gives us something that is approximately variance 1. Okay, and so remember, the only thing is we don't have sigma, and so we plug in its estimate, sigma hat. Okay, so this studentized residual is approximately, so we can say that these are standardized to have approximately variance 1. Okay, so as we talked about in residual analysis, we realized that the residuals aren't quite IID with variance sigma squared, but the residuals have a distribution with variance that is actually affected by the hat matrix. Okay, so therefore by dividing by this part, we do have residuals that approximately have variance 1, and so based on the studentized residuals, we can identify outliers in terms of the response. Okay, so if di is very large, okay, so either very positive or very negative, then we can consider those to be outliers in the sense of having an extreme value of the response. Okay, and so because these are, this is approximately variance 1 and, it's almost a standard normal, well, we know that in a normal distribution, most of your data lies within 3 standard deviations of the mean. So here we're looking at, okay, so approximately variance 1. So we're talking about plus minus 3 is a good rule of thumb for considering when these values di are either very negative or very positive. Okay, so point here then is that so if the absolute value of the studentized residual is large, that means we have an observation that is extreme. We can capture a point like point A here. Okay, it's the value of the response is far away from the rest of the data. If we were to fit a regression line, then the residual would be quite large, and so this is the what di is able to capture here. Okay, so if this is large, then observation I might be considered an outlier. In the sense of having an unusual or extreme value of the response. Okay, so that's yi. Okay, and then a good rule of thumb is, as I mentioned, greater than 3, because that's, we know 99-point-something% of data would fall within 3 standard deviations of the normal. Okay, and so this corresponds to case A here. Okay, case A in this graph. Okay, so that's one form of outlier. So if the response is pretty extreme, then we'll be able to measure it by calculating the studentized residual, which accounts for the differences in these variances of the residuals. So it standardizes for that. So then we can compare them all on the same scale, and so therefore, when they're large, so like less than -3 or bigger than 3, we can consider them to be quite extreme. Okay, now second, let's look at point B now. Okay, so this is now talking about a new concept, which is called leverage. Okay, so recall that HII is the ith diagonal element of our hat matrix H. Okay, so on your homework, your assignment 3, I asked you to do a few exercises concerning this hat matrix and to investigate some of its properties. Okay, and so we're going to make use of a bit of that as we talk about this concept of leverage. Okay, so we're going to call HII. So this this is for the ith diagonal element corresponding to ith observation. Okay, we're going to call this value the leverage. observation I. Okay, so let's unpack that a little bit and see why that is helpful. Okay, so first we have the fitted values. So we have mu hat, so the vector of fitted values. Okay, we know we get that by taking x times the parameter estimate beta hat, and we learned that this is after we write out the beta hat, we know we have x, and then we have x transpose x inverse x transpose y. Okay, and then this is the part that we call the hat matrix. Okay, so this is H y. Okay, so what can we say about one particular fitted value? Okay, so let's say, so what is mu hat I? So the ith fitted value. Okay, well we can therefore express it in terms of this multiplication of the hat matrix times the fitted value vector. Okay, so how do I get the ith one? Well, I need to take the corresponding row in H. Okay, so it's going to be hi1. So this row vector hi1 up to hin. Right, and then I'm going to multiply that with corresponding y vector, so y1 to yn. Okay, so that's how I get so this is the ith row of H times the vector of observations y. Okay, so that's what it looks like in terms of getting the ith entry from H times y. And so if I actually multiply this out, well, it's so of course it's simply H. It's okay. So let's write out what it is first. So okay, so we know this comes out to be Hij times Yj. Okay, and for convenience and to explain this concept, I'm going to pull out the ith term out of here. So I'm going to have Hii times Yi, and then plus the rest of them. So j not equal to I, Hij, Yj. Okay, so the reason for doing that is from this expression, we can see that the fitted values, so the fitted value can be expressed in two parts. There's one part which is based on the corresponding value of the observation. Okay, so mu hat I, of course, is going to be related to the observation because remember yi minus mu hat I is the residual. Okay, so so we can start to see the role that Hii plays in this in determining how close the fitted value is to the corresponding observation. Okay, so in this expression we see that if Hii is like close to 1, then and the rest of the Hij's are small, then the fitted value is going to be quite close to the corresponding observation, which means the residual for this observation is going to be small. Okay, so let's write that out in words. Okay, so looking at this expression, we see that Hii, so the leverage, captures the contribution of the corresponding observation. Captures the contribution of Yi in determining its corresponding fitted value. Okay, so in particular, if the leverage is high, large, relative to the other elements in the second part here with the sum, relative to hij's, or j not equal to I, then that means mu hat I, the fitted value is mostly determined by the observation itself. Is most by yi. Okay, now in your third assignment, you will be able to show that the leverage lies between two bounds. So as upper bound and a lower bound, you will show that the leverage lies between 1 over n, where n is number of observations. So that's the lower bound, and it also has an upper bound, which is 1. Okay, so with that in mind, then that means 1 is the largest possible value of the leverage, which also makes sense because remember that if the leverage is large in the sense that it's close to 1, then the variance of the residual, okay, so remember the expression for that was sigma squared 1 minus the leverage, okay, 1 minus hii. Okay, so if hii is close to, of course, this variance has got to be non-negative. Okay, so but if this leverage is very high, then that means this variance is going to be close to 0. Okay, so and if that's the case, which in turn implies that the residual for that observation is going to be small. Okay, so yi is going to be not far from the corresponding fitted value. So in words, the residuals of observations with high leverage tend to be small. Okay, so again, let's give a rule of thumb for how to characterize what's considered a large leverage. Okay, so as a rule of thumb, an observation with leverage greater than twice the average leverage is considered high. Okay, so what, in notation form, that means hii is greater 2 times the average leverage, which I'll call H bar. So what is H bar? Is simply the average of all the leverages, so this is 1 over n. Plus 1 and then H. So this is the average. H bar is the average leverage. Okay, and so what is this part? Well, what is the summation of all the leverages? Okay, so actually we know the answer to that because the hat matrix is idempotent, and so therefore the trace. Okay, so this is the trace of H, and we claimed last time that the trace of the hat matrix is equal to the rank of the matrix of predictors X, and that is P plus 1. Okay, and so therefore this fact, again, you're going to fill in the blanks to finish this proof on your third assignment. Okay, so therefore this sum of all the leverages is the sum of all the diagonal elements, is the trace of the hat matrix, P plus 1. And so we can actually fill in what this is. So 2 times H bar is over n is 2 times P plus 1 over n. Okay, so that gives us a rule of thumb for when a point is considered to have a high leverage. Okay, so remember that the hat matrix only involves the matrix of predictors X. Okay, so let's write it again. It's X times X transpose X inverse X transpose. Okay, so the key thing to note here is only involves the predictors. Okay, so in order to calculate the hat matrix, we don't actually need to know the values of the response. Okay, the H matrix is computed solely on the basis of the predictors. Okay, so leverage. So in other words, leverage is based on looking purely at the predictors. It doesn't tell us anything about the response. So in fact, what leverage is able to do is we can use leverage to detect outliers in the explanatory variable. So if an observation has a value of xj that is very far from the others, it will tend to have a high leverage, and the value of HII will be relatively large. Okay, so let me write that down first. So that only involves the predictors and not the response. Okay, and so thus leverage is useful for finding outliers in the values of the explanatory variables to help outliers in the sense of having unusual or extreme values in the explanatory variables. Having explanatory variables with extreme or unusual values. Okay, well, I'm making this claim, but I haven't, of course, shown algebraically why that's the case. But intuitively, we see that leverage only calculates quantities based on based on the predictors and not the response. Okay, so in order to see that, well, again, let's give you some intuition by looking at the simple linear regression case. Okay, so since it's useful to identify outliers, so for example, see point B in our plot. Okay, so what does the expression, the HI look like? So in simple linear regression case, we can actually simplify this calculation. So we can actually calculate this matrix and look at how HI can be expressed in terms of the elements of X, which is something you sort of did. So you did in simple linear regression on your last homework. I asked you to manually calculate X transpose X inverse when you only have one predictor, and then look at things like the covariance matrix. Okay, so by a similar kind of calculation, we can simplify this in the case of simple linear regression. Okay, so what is this ith diagonal element in terms of the values of X? So it ends up looking like this. It would be 1 over n, and then plus xi minus x bar squared. Okay, and then on the bottom is the sum of squares x. Okay, so this requires some algebra. After some algebra, okay, so what does that tell us is, well, what are the observations that are going to have high leverage? Well, again, you notice you have this 1 over n here. Okay, well, why does that make sense? Well, because we claimed, and you will show formally, that the leverage has to be, the lower bound is 1 over n, so it's going to be 1 over n in this case, plus something which is non-negative. Okay, so you see if xi is close to the mean of the average value of the predictor, then this term is going to be small. But if xi is far away from x bar, so in other words, the value of x for that particular point is very far away from the rest of the points. Okay, so this difference is large, then it's going to correspond to having a high leverage. Okay, so let me finish writing this. So intuitively then, which means if xi is far from x bar, that point will have high leverage. Okay, and this also generalizes. So coming to the question, if we have high leverage, is that an indicator of potential outlier in terms of the predictor? Yes. So in the simple linear regression case, the algebra works out a little bit nicer, and we can see that effect explicitly. So xi is far from where the rest of the points are, as measured by the mean, then it's going to have a high leverage. Therefore, it is an outlier in the x dimension. Okay, so this generalizes to multiple linear regression. A point in the sense that an observation with high leverage. Okay, according to this, for example, using this rule of thumb, like twice the average leverage, will be considered an outlier. Is an outlier with extreme values in one or more explanatory variables. Okay, so therefore that completes the story for leverage, and so high leverage would help us pick up this point B here, would have a high leverage in this example. Okay, but I do want to, and I also want to emphasize that because this is based on the hat matrix only, it doesn't tell us directly whether this point is an outlier in the response dimension or not. Okay, so let's just put this as an additional note. Okay, but leverage doesn't tell us. Directly whether that observation is also outlier in the response. Okay, and why is that? Well, remember when we first wrote down that formula for HII, we realized that when the leverage is high, the observation actually will be close to the fitted value. So in fact, we will actually generally not see this just by looking at the leverage calculation. Okay. In fact, as we noted, the fitted value will. So in other words, the regression line will actually be often quite close to the actual value for points with high leverage. For such observations. That should be clear for such observation with high leverage. Okay, so that should state all what we need to know clearly. So we see that points with high leverage tend to have lower residuals. So in other words, they are you can think of them as in some sense at least pulling the regression line towards that point. So hence the term leverage. Okay, so that takes care of cases A and B. Now finally, which the last one we're getting to. Okay, so the last type of outlier is ones that are outliers in both the sense of the explanatory variables and also in terms of the response. So in fact, this case C is actually the most influential outlier in the sense that outliers that look like this tend to actually have the greatest effect in terms of the estimates for your fitted model. Okay, and so that alludes to this concept we're going to talk about next, which is influence. Okay, so points like C are actually quite influential in the sense that they're going to affect what we actually get out of our regression parameter estimates. Okay, so let's look at the last thing, which is how to identify points like C here. Okay, so the concept is called influence. Okay, so we say that so an observation I is quite influential. We say if its presence in the regression model in fitting the regression model considerably changes what we get in terms of the parameter estimates. Considerably changes the estimates compared to compared to when that observation is not used to fit the model. Not used. Okay, so that's what we mean by influential. So by having that point in the data set and used as part of calculating our least squares estimates, that's going to change our parameter estimates on beta hat considerably. Okay, so that's what we call an influential point. Okay, and so let's unpack this concept. So the key idea we're working towards is, well, when is a point going to be influential? So it turns out it's related to the two concepts we talked about already. So it's actually going to be related to studentized residual, and also it's going to be related to leverage. In fact, the conclusion we're working toward is that if a point has both a large studentized residual and also a high leverage, those are the points that tend to be influential. Okay, so let's work towards that and then unpack this a bit. Okay, so let's start with fitting our regression model. Okay, so start with fitting y equals x beta plus epsilon. Okay, so we're going to start with our regression model using all the data. Yeah, so all the observations we have. So and call the estimate and call the estimate of beta hat as usual. Via least squares. Okay, and so to measure influence, okay, so to formalize this idea, we want to look at how much does beta hat change if we take away the ith observation from fitting the model. Okay, so let's define that more formally. So let's call it beta hat, and I'm going to put here bracket I. Okay, so let that denote the least squares estimate. Based on fitting the model with the ith observation removed. So, okay, so this one is based on n-1 points. Take out the ith one. Okay, and so the key idea then is if this beta hat I is quite different from beta hat, then this is what we mean by an influential point. Having I in the model versus not in the model actually changes the regression estimates for beta. Okay, so that's formally what we mean by influential. Okay, so the idea is then, okay, so the idea of influence is if beta hat without observation I is quite different than beta hat based on all the data, then observation I is highly influential. Okay, and so any time you have what do you mean by quite different? Well, of course that is reminiscent of the kind of things that we can do with a hypothesis test and asking whether whether beta hat I is significantly different from beta hat. Okay, and so to do that, well, we won't get into all the details of testing this hypothesis, but we'll first, of course, need some statistic to measure how far beta hat I is from beta hat. Okay, so to do that, we define a measure that's called Cook's distance. Okay, so we can measure this using Cook's distance. So it's the distance between these two parameter vectors, between beta hat and beta hat, estimated without the ith observation. Okay, so we're going to call this quantity capital DI. Okay, so that'll distinguish it from little di, which we're using for studentized residuals. Okay, so di is calculated like this. So this is the definition of Cook's distance. We take the difference of these vectors, okay, transpose. Okay, and then we're going to put x transpose x in the middle. Okay, we'll see why that makes sense in just a moment. Okay, and then we have beta hat I minus beta hat. Okay, so that's what goes on top. And on the bottom, we have a scaling factor, which is sigma hat squared, and then p plus 1. Okay, so intuitively, what this is doing is it's taking the difference between these two parameter vectors, and it's applying a metric on it. Okay, so what metric is actually doing is, well, actually by having x transpose x in the middle, that actually scales. That scales the parameters to be on the same. Takes the parameter estimates and scales them to use the scale of the fitted values. Okay, so to see that, let me just show you why that's the case. To see some intuition. Okay, so let's say mu hat. Okay, I'm going to use the same notation. So mu hat. So let this one be the fitted values if we were to remove based on the parameter estimates without that point. Okay, so that's the fitted values based on removing the ith and estimating theta. Okay. Then we notice that, well, we can multiply some of this stuff through, right? We can take this x transpose and put it into the first term, and then we'll take this x and put it into the second term. Okay, so therefore we see that di is actually takes the beta hats and it applies and applies the predictors to them, so that we're basically comparing a metric on the corresponding fitted values. Okay, and so based on this, then we see that di. Okay, so now we distribute this in here. So this becomes okay. So we'll have x beta hat I minus x beta hat transpose, and then we put the other x onto the right hand side term. I, and then so sigma squared. Sorry, p plus 1. Okay, so I've distributed the x. This x is in the middle to the two sides. So we see that this becomes the difference of the fitted values with and without observation I for estimating beta. Okay, so in terms of what we just wrote, this would be mu fitted values mu at I, okay, and then minus the usual fitted values, transpose, and then mu hat I minus mu hat p plus 1. And what is this? Well, now you just have this vector difference, transpose, and the vector. Well, this is just a measure of the Euclidean distance. Okay, so this is you can think of this as mu hat I minus mu hat over this scale factor. Okay, so in other words, this is how we can interpret Cook's distance. Di measures the Euclidean distance between the fitted values of these two regressions. The two regressions that give us mu hat I, which is take out the ith point, and the usual mu hat based on all the data. Okay, up to, and then there's a scaling term at the bottom, up to scaling factor. Okay, so that's the interpretation of Cook's distance. All right, so now we're going to look at this a little more closely next time, and I'll show you the relationship, as I promised, to that Cook's distance is related to the two concepts we looked at just prior, studentized, residuals, and also leverage. Okay, so in fact, those two concepts, so HII and DI, play, from the studentized residual, play a key role in the calculation of DI. Okay, so I'm going to show you some of these details next time. But suffice for now, let me give you the conclusion. So it can be shown that, okay, so that's the interpretation in terms of the fitted values. And further, shown that DI, so the Cook's distance, is related to these quantities. All right, so it's going to be the square of the studentized residual times the leverage over 1 minus the leverage And then finally we have that, we still have this 1 over p plus 1. Okay, so I'll defer the proof to this for next time. But let me comment on this expression and what we can learn from it. Okay, so based on this expression, where we can see that both di, so the studentized residual, contributes to the Cook's distance, and so does the leverage. Are the key quantities to calculate di. Okay, and so we have a di squared here. So therefore, whether you have a highly positive or a highly negative residual, that's going to increase Cook's distance. So yes, that's the first thing. And likewise, if HII is close to 1, again, this is an increasing function of HII. Okay, so therefore, these two work together to give us a large Cook's distance. Okay, and observation I will be the most observations, let's put it this way, observations that are the most influential would have large values of the studentized residual and high leverage. Okay, so we see that relates to what we've been talking about. So if an observation, I should put the absolute value here. Fix that. Okay. Because high absolute value corresponds to a high value of di squared. Okay, and so remember that, based on what we discussed today, a high value of absolute value of the studentized residual and a high value of leverage. Okay, so remember what these things imply. So it's high di, this is an outlier in the response. And if a point has a high leverage, as we discussed, this is an outlier in the explanatory variable. Okay, so therefore we now see which are the most influential points. So what points are actually going to affect our estimate of the regression coefficients beta hat the most? Well, the points that are high absolute residual and also high leverage. In other words, they are the points that tend to be outliers in both dimensions. So this is a way to characterize this point C on the plot. This is this would be considered an influential point. It has a high. It's going to have a high residual and also a high leverage. Okay, so that's the key message from here. Okay, so highly influential points in the sense of affecting on parameter estimates tend to be outliers in the sense of having both extreme let me rephrase is that having extreme values in both the response and one or more predictors. Okay, and so therefore we have now shown that this influence can capture a point like C. Point C on our plot. Okay, so again, we can just look at, so we can check if some of these Cook's distances, di's, some di's are much larger than the others. Okay, as those, they would be the most influential observations. Okay, so that's what I wanted to discuss today. So let me just pause to see if there are any questions before we log off and call it a day. Okay, so on Wednesday, we'll be back on stream to do this proof for Cook's distance, and then I'm going to show you some examples in R, and so I will see you then.